I'm a mechanical engineer. I think a lot about manufacturing and the importance of manufacturing to our world and where manufacturing is headed in the future. And I've seen interest in manufacturing grow at MIT since I came here as faculty in 2013. And that's really exciting given all that MIT can bring to the table. And this chart emphasizes how advances in manufacturing have changed the course of history. Now, maybe we're beyond the time where one invention, one innovation can do that, but Gutenberg's printing press in the 1400s, printing of books using movable type, and the manufacturing process, the casting process that made that be possible, spread information across Europe and around the world. Or the Siemens Bessemer process for open hearth manufacturing of steel in the late 1800s, in the Industrial Revolution at the time. And even the Wright brothers airplane, not made in quantity, but the engine block was made of a lightweight aluminum alloy, and manufacturing helped enable the plane to take off. Manufacturing is also really hard. Lego bricks are among my favorite things, and think for a moment about how you would describe how to manufacture a Lego brick. You may know that it's made by injection molding, a very widely used process where molten plastic is squeezed into a mold. When the plastic has cooled, has frozen, the mold opens up and the brick drops out. I just described it to you to one level, but now think about how you would explain how to make the surface so smooth, the dimensions so accurate, and the bricks so consistent that they will all fit together no matter what size and shape. And now imagine how one would describe the manufacturing of something as sophisticated as an iPhone. My endpoint will be that while I'm very much a hardware guy, a mechanical engineer, I see the intersection of computing and manufacturing helping solve this challenge and create immense opportunity. And we're also faced with fragmentation of manufacturing. We're at a place in the world where there's a lot of discussion about manufacturing's importance and how manufacturing has evolved over recent years and decades. And we also struggle with transfer of that information. Apple, no matter how large, even if it chose to manufacture itself, cannot make all the parts and pieces. It's just not possible. So we've gone from, in a way, vertical integration of manufacturing to fragmentation of manufacturing. And I think we can bring that back together no matter where it happens. So a central question to me in my research and other activities is how can we collapse this complexity? When I came to MIT in 2013 as faculty, I began thinking somewhat serendipitously about 3D printing. MIT's first work in 3D printing was done in the late 1980s. Our colleagues at MIT actually coined the term 3D printing around that time. Now, 3D printing is not a way to make even a large fraction of all the parts and products that we use. Look around the room, you don't really see any 3D printed parts, but I'll tell you how I feel it is transformative as a principle in some important contexts. And you may know that 3D printers stretch from those you could use on your desktop or in your garage to heavy-duty industrial metal printers. And I'll tell you about my perspective through the story of starting a company with a student who I met in my first semester at MIT, a student in this program, which is a master's program in manufacturing and design in the Mechie department at MIT. After I taught a class on manufacturing processes to the students in this program, I stayed in touch with the cohort, and with a few of those students, we brainstormed about addressing the barriers that prevented 3D printing, particularly of metals, very high performance materials, from being brought to industrial scale. A few years later, we formed a company called Vulcan Forms. Now, 8 years ago was that founding date, and today we have a factory of about 150,000 square feet, an hour west of Boston, that's full of industrial scale metal 3D printers and corresponding equipment, and printers that the company designed and built itself. With these machines, we can print medical implants, the kind of implants that are in millions of people today. This is what's called the acetabular cup, a component of a hip implant, what you get in your body if you get a hip replacement. It's not just making one at a time, it's making about 140 at a time on one plate. And the same machine, arguably by changing just one line of code, can make a component of a jet engine, or can make 550 or so housings for watches, potentially smart watches. And I have the parts right here in my hands. Here's a picture of one of the machines, and it's powered by lasers. So it's literally electricity plus information, bits, plus a general raw material, metal powder, that makes these parts possible. And behind the machine, you have not just one laser, but a rack of lasers. It looks kind of like a server rack that does compute, but these are actually lasers, and light comes out of each of the fibers that's plugged into the numbered boxes that you see. And if you walk into the factory, it doesn't grind, it hums. It sounds like a computing facility. Along the way, looking back at how the company was built, the software and the so-called digital stack or digital thread was also key. So before a part is ever printed, such as the watch housing in my hand, we're able to simulate the process. That's because when you do 3D printing like this, you generate a lot of heat. The lasers melt the metal, the heat builds up, and you have to understand the impact of that on the material properties and the deformation, the distortion of the part. So it doesn't crack, it doesn't break, and you don't have too many defects that can compromise the properties. So we built and adopted software tools to simulate the process, to virtually lay out the print, and then when the printing starts, we do a relatively straightforward thing that's really important. The printer takes pictures every time it completes a layer, and then on the fly looks for microscopic flaws. And the process runs uninterrupted if flaws aren't detected. If flaws are detected, it can identify ways to correct for those flaws. And at the end of the print, there's a digital twin of the printed geometry that can be compared to the expected outcome and can also be used to train the system over time. And 3D printing is rarely the only thing you need to do to make a part or a product, right? Few products have one part, and even something like this, to make it look like something a consumer would buy, you need to finish the surface. So we integrate machining with 3D printing in a separate step, but with integrated software tools. So we design the part to be printed with just a little bit of extra material, and then in a short time in a CNC machine, a milling machine, the excess is taken away. The last part is the control of the machines is now centralized. So you need humans to unload the machines, maintain them, do a lot of the downstream steps, but the printing process itself brings the information in real time from all of those huge printers to one control desk. And one or two people can sit there and watch the operations and be alerted when there's something that requires their attention. And that has enabled better quality, higher productivity. In my lab at MIT, we're active in this area as well, and one very active area is identifying new materials for use in 3D printing and other manufacturing processes. 3D printing of this and other types has unique characteristics, such as when a laser melts the metal, it heats it and cools it very, very quickly. That traps certain conditions, microstructure. And in the case of aluminum alloys, we've developed a numerical technique to search a lot of possible combinations of elements and come up with a family of alloys that have better properties mechanically, higher strength and higher temperature resistance than well-established materials. And as 3D printing as a manufacturing technology for high-value parts grows, it'll be a way to onboard new materials with unique properties faster, such that we no longer say, I want this specific material, but we say, I want this specific property or combination of properties, and a material can be tailored and custom formulated for that application in a way as we think about perhaps personalized or tailored medicines in the future. A few years ago, I read a paper that became very influential to me, written by Rebecca Henderson, who's a professor at Harvard. And she was a PhD student at MIT when she wrote this paper. And it introduced the term architectural innovation. And the paper says that the essence of architectural innovation is the reconfiguration of an established system to link together components in an existing way. And while there are many new technologies, I feel like in some way we're faced with new technologies and possibilities in increasingly astounding ways. In my opinion, a lot of innovation is that of the architectural type. We take established capabilities and we put them together in new ways to create new possibilities. That's in a way what SpaceX did, what Amazon did, what TSMC did, brought new capabilities by thinking at the system level. Speaking of TSMC, we hosted Morris Chang, the founder of TSMC, here for a talk about a year ago, and he reflected on his career as the founder of TSMC, the most important semiconductor company in the world, and described how TSMC reconfigured the boxes of the semiconductor industry, established shared manufacturing capacity, and then cultivated an ecosystem around it. And I feel that's what will happen as computing and AI converge with manufacturing going forward. So I have this very simple view that I'll leave you with, that we'll see advancement in digital-ready and digitally enabled production tools, and advancements in tools that allow humans to interface with design and manufacturing. And as there's more and more progress in multimodal AI models, models that can handle not only text but images and video and incorporate physical simulations, we'll be able to stitch all of these together and rethink how manufacturing is done, where it's done, and what products are possible in important ways. So back to that idea of, how do you describe the manufacturing of a Lego brick or something much more complex in the future? I think it will be very possible, and there'll be three broad implications. The first is we'll see completely new product designs. This is, of course, the SpaceX Raptor engine, and SpaceX has adopted 3D printing quite intensely to drive rapid iteration and rapid development and a convergence of design and manufacturing. Going from Raptor 1, 2, to 3 is an incredible transformation and also a simplification. So the complexity has in large part been collapsed and the manufacturing has been condensed. But instead of manufacturing being dedicated, manufacturing will become more flexible. If I may use the example of the industrial 3D printer, switching its code to make medical implants, jet engine parts, or smartwatch housings, we'll have facilities and factories, whatever size they are, that are flexible and can change what they make more responsively and at a limit on demand. And last, it changes the value chain. A lot of how companies make decisions and perhaps how policies are set are based on a perception and a reality of how value is distributed. Owning the design versus owning the manufacturing and the relative economics and value add along the stream. And incorporating more digital technologies, more automation in one way can boost the value of production as an information-driven asset, and I feel that has very important implications that we're just scratching the surface of. Thank you.